Welcome to today's deep dive. If you're joining us, it means you probably have a healthy curiosity about some of the really big questions out there.
Yeah, the biggest ones, really.
Exactly. And today we're setting out on a very specific mission. We are unpacking a highly debated philosophical and scientific argument regarding the origins of the universe.
Right.
And we're drawing from excerpts of a book by authors Norman Geisler and Frank Turek. Specifically, we're looking at something called the teleological argument.
Oof. Which I know that is a hefty term, but it really just stems from the Greek word telos, which simply translates to design or purpose.
Okay.
The fundamental premise that Geisler and Turek put forward is actually pretty straightforward. It's the idea that every design implies a designer.
Right, right.
They make the case that the universe exhibits an incredibly complex, finely tuned design, and therefore, the universe must have a designer.
Yeah.
It's essentially a modernized take on William Paley's famous watchmaker analogy.
Oh, yeah, the watchmaker, where if you're walking through the woods and you find a complex mechanical watch lying on the ground.
You would never assume the wind and the rain just randomly eroded the soil into the shape of interlocking gears.
Right, with a glass face and everything.
Exactly. You assume an intelligence created it.
Okay, but a watch is obviously manufactured. I mean, we know what a watchmaker is. A forest or a giant galaxy isn't manufactured in a factory. So how does the book make that leap from a mechanical watch to a natural, sprawling universe?
Well, that's the exact leap they try to bridge with modern cosmology. They argue the universe is essentially the ultimate intricate watch, tweaked with just mind-boggling mathematical precision to enable human life. It's an argument based very heavily on statistical probability.
Now, before we get into the statistics, we do need to offer a quick disclaimer about the tone of today's deep dive.
Yeah, that's important.
The source material we're working from makes very strong, very specific arguments in favor of divine design, and it strongly critiques atheism.
Very strongly.
Right. So our goal today is not to take a side or tell you what to believe. We're simply going to impartially explore how this text uses science, statistics, and history to build its case. That way, you can evaluate the logic and the evidence for yourself.
Precisely. We're acting as your guides through the mechanics of their argument. And they don't just rely on abstract physics to make their point. They introduce a concept called the Anthropic Principle.
The Anthropic Principle.
Yeah, which is the scientific observation that the universe appears perfectly fine-tuned to support human life. And to bring this abstract concept down to Earth, or rather, into orbit, they frame their argument around one of the most thrilling and, frankly, terrifying moments in NASA's history.
Apollo 13.
Apollo 13.
The way the text uses Apollo 13 as a framing device is highly effective for understanding these complex physical laws. So let's step back to April 13th, 1970. We are exactly 55 hours and 54 minutes into the mission. Commander Jim Lovell, pilot Jack Swigert, and pilot Fred Hayes are hurtling through the vacuum of space at over 2,000 miles an hour, heading straight for the moon. Everything is functioning perfectly.
Right. Lovell even described the crew's mood as fat, dumb, and happy.
Yeah, he's putting some wires away right after a live TV broadcast, and suddenly a loud bang shakes the spacecraft.
And initially, the crew doesn't even realize the severity of it.
Mm-hmm.
Lovell actually thinks Swigert is secretly actuating a noisy valve to startle them as a joke.
Just messing with them.
Yeah. But then we get that legendary chilling radio exchange with Charlie Duke down at Mission Control in Houston. Swigert says, "Houston, we've had a problem here."
Duke asks him to repeat the transmission.
And Lovell chimes in with a vital piece of diagnostic information. He says, "Houston, we've had a problem. We had a main B-bus undervolt."
Let's pause there to translate the jargon. A main B-bus undervolt. In plain English, half their electrical power system just crashed. The spacecraft had two main power buses, A and B, which distributed electricity to all the vital systems. Losing one meant a massive immediate crisis.
And it cascaded from there. Fred Hayes notes the voltage looks okay for a second, but then mentions a sensor on oxygen tank 2 is oscillating wildly from 20 to 60% before it just spikes to full-scale high.
The master caution warnings are blaring.
Yeah, 2 of their 3 fuel cells are completely dead, and the third is dying fast.
Then Lovell looks out the hatch and reports the ultimate nightmare. He tells Houston, "We are venting something out into space. It's a gas of some sort."
That gas, of course, was their precious oxygen. Tank 2 had violently exploded, and the blast actually damaged Tank 1 in the process. Now, to connect this to the bigger picture the book is drawing about fine-tuning, we have to look at the root cause of this explosion.
Okay.
This catastrophic quadruple failure of interdependent systems wasn't caused by a massive meteor strike
Yeah.
or some fundamental design flaw in the spacecraft. It was caused by a drop of just 2 inches.
Just 2 inches.
Yes, 2 inches. Prior to installation at the factory, oxygen tank 2 had been accidentally dropped 2 inches.
Wow.
And that tiny jolt slightly damaged a thin internal fill tube. Later, when they tried to boil off excess oxygen during a routine ground test, the damaged tube caused a heater switch to weld shut.
Oh, no.
It baked the Teflon insulation completely off the wires inside the tank. So once they were in space, when Swigert flipped a switch to just stir the oxygen, those bare wires short-circuited, sparked, and blew the tank apart.
That seemingly insignificant 2-inch mistake nearly killed the crew because their spaceship was a strictly interdependent system.
Exactly.
Without oxygen, the fuel cells couldn't chemically combine oxygen and hydrogen to create water and electricity. No air, no water, no power.
Right.
And the text compares our planet Earth to that Apollo spacecraft. We're this tiny oasis hurtling through a vast, lifeless, hostile void. And just like Apollo 13, the book proposes that the universe relies on incredibly delicate, interdependent constants to sustain us.
Which brings us directly to the anthropic constants. These are the highly precise, interdependent environmental conditions that make up the anthropic principle we mentioned earlier.
Right.
The text uses the specific crises aboard Apollo 13 to highlight how fine-tuned our own global spacecraft truly is. Take oxygen levels, for example. On Earth, oxygen makes up exactly 21% of the atmosphere.
And the book details the tightrope we walk with that exact percentage. If oxygen levels were just slightly higher, say, at 25%, fires would erupt spontaneously all over the planet. The atmosphere would be highly combustible.
Which is terrifying.
But if it dropped to 15%, human beings would suffocate, which mirrors the terrifying reality those Apollo 13 astronauts faced as their tanks emptied into the vacuum of space.
Then there is the issue of atmospheric transparency.
The re-entry window.
Yeah, as the crew tried to navigate their crippled, freezing ship back home, they had to hit an incredibly narrow re-entry window into the Earth's atmosphere. They had to aim for a point no less than 5.5 degrees and no more than 7.3 degrees below the horizon.
That is such a tiny margin of error.
It really is.
Right.
Any shallower, and the spacecraft would skip off the atmosphere like a stone on a pond, sending them into deep space forever. Any steeper, and the friction would cause them to burn up.
And to hit that window, they needed a completely clear view of the stars to manually align their navigation instruments. The text points out that Earth's atmospheric transparency is another finely tuned constant.
How so?
Well, if our atmosphere were less transparent, we wouldn't receive enough solar radiation to keep the planet warm or allow plants to grow. But if it were more transparent, we'd be bombarded by lethal cosmic radiation.
The parallels just keep continuing with the moon, too. Apollo 13 famously had to use the moon's gravity to slingshot back toward Earth. The text uses this to highlight the constant of Moon-Earth gravitational interaction.
Okay.
If the gravitational pull between the Earth and the Moon were greater than it is right now, the tidal effects on our oceans would be catastrophic. It would flood continents, and it would severely alter our rotational period.
But if that gravitational pull were less, it would cause severe climatic instabilities. The moon actually stabilizes the Earth's wobble. Without it, the climate would swing wildly, making complex life nearly impossible to sustain over long periods.
We also have to look at the carbon dioxide problem.
Oh, this is one of the most tense moments from the Apollo 13 crisis.
Yeah. The astronauts were crammed into the lunar module, which was only designed to support 2 men for a maximum of 40 hours. Now, it had to support 3 men for 4 days.
Right, and with every breath, their own exhaled carbon dioxide was building up to lethal levels in that tiny cabin. Mission Control told them to use the extra CO2 scrubbing filters from the powered-down command module, but there was a major engineering mismatch.
The famous square peg.
Exactly. The command module filters were square, but the lunar module's environmental system only took round filters. It's the ultimate literal case of fitting a square peg into a round hole. Flight director Gene Kranz famously reacted by saying, "Tell me this isn't a government project."
Yeah, and ground control had to invent a crazy workaround, using cardboard torn from flight manuals, spacesuit hoses, stowage bags, and duct tape.
Just duct tape and manuals.
Yeah, so the astronauts could build a makeshift adapter. And the text parallels this desperate struggle for balance to Earth's carbon dioxide levels. On Earth, CO2 levels are perfectly maintained by nature. If the level were higher, We'd experience a runaway greenhouse effect and burn up. If it were lower, plants couldn't maintain efficient photosynthesis, the food chain would collapse, and we'd basically suffocate.
Finally, in the Apollo narrative, there is the sheer terror of re-entry. The astronauts were falling back to Earth, accelerating to nearly 25,000 miles per hour, pulled by Earth's gravity. The text lists Earth's specific gravitational force as yet another constant.
Because if the gravitational force were altered by even a tiny fraction, our atmosphere would either fail to retain vital water vapor, or if the gravity were stronger, it would retain too much lethal ammonia and methane.
And the book doesn't stop at those 5 constants either. It goes on a rapid-fire tour of the cosmos to show how many of these precise conditions exist. For instance, it describes Jupiter as a massive cosmic vacuum cleaner.
Right. Which sounds like an odd metaphor until you look at the mechanics of our solar system. Jupiter is a massive gas giant with an immense gravitational field. Because of its size and its specific orbit, it attracts a huge percentage of the stray asteroids and comets flying through our solar system.
So it's protecting us.
Exactly.
Yeah.
If Jupiter wasn't exactly where it is, Earth would be constantly bombarded by catastrophic space debris.
The text also points to things we usually view as purely destructive, like earthquakes. Earthquakes are obviously devastating to human life, but the book argues that without tectonic activity, the planet would be dead. Why is that?
It comes down to nutrient cycling. Rains wash vital minerals and nutrients off the continents and into the oceans. Over millions of years, the land would just become barren. Tectonic activity, the shifting and colliding of the Earth's crust, is what forces the nutrient-rich ocean floor back up to the surface over geologic time. Without that constant churning, the soil wouldn't support life.
They also point to the precise 23-degree axial tilt of the Earth and our 24-hour rotation. If our rotation took significantly longer, the temperature extremes between a prolonged day and a prolonged night would be unsurvivable.
And if it were shorter, atmospheric wind velocities would whip into constant disastrous hurricanes.
They even zoom all the way out to the initial expansion rate of the universe itself right after the Big Bang. The text states that if the universe had expanded at a rate 1/millionth more slowly than it did, gravitational forces would have caused everything to collapse back in on itself before stars or planets could even form.
A millionth of a fraction slower.
So when you put all these interdependent systems together, what is the mathematical takeaway? The authors bring in astrophysicist Hugh Ross, who calculated the probability of 122 of these anthropic constants existing simultaneously for any single planet by pure chance.
The statistical argument here is the absolute core of their teleological proof. Ross calculates the probability of all 122 constants aligning randomly to be 1 chance in 10 to the 138th power.
Wow.
That is a 1 with 138 zeros after it.
Which is a number so large the human brain literally cannot picture it.
Exactly. To give it some scale, the text points out that scientists estimate there are only 10 to the 70th power atoms in the entire observable universe.
Wait, atoms?
Yeah, total atoms in the universe. Meaning the odds against our precise, life-sustaining environment happening by accident are trillions of times greater than the number of single atoms in existence.
That's incredible.
The authors use this to argue that there's effectively zero chance of our planet existing by a random roll of the cosmic dice. They quote Nobel laureate Arno Penzias, who actually co-discovered the cosmic radiation afterglow of the Big Bang, who said that these precise observations suggest an underlying supernatural plan.
So if the mathematical odds are that statistically absurd, how does a secular or atheist perspective counter it? The source text addresses this by introducing the multiple universe theory, often called the multiverse.
Right.
To use our Apollo analogy, imagine if NASA told the public that Apollo 13 surviving had nothing to do with brilliant engineering or careful design. Instead, they claimed they actually launched millions of Apollo 13s, and statistics dictate that at least one of them was bound to make it back safely by pure chance.
That is a perfect way to conceptualize it. The multiverse theory posits that there isn't just one universe, but an infinite number of universes in existence. Because there are infinite universes, every possible set of conditions, no matter how improbable, is bound to happen somewhere.
So we shouldn't be surprised.
Right. Therefore, we shouldn't be surprised by our fine-tuned Earth. We just happen to be incredibly lucky to live in the one universe that rolled the exact right conditions for life.
But Geisler and Turek strongly push back against this counterargument, and they break their rebuttal down into a few distinct critiques. First, they argue there's simply no empirical evidence for it.
None at all.
They note that all detectable, finite reality began with the Big Bang. Because we cannot observe anything outside our universe, they call the multiverse theory a metaphysical concoction built entirely on assumption rather than observable science.
They also make a deep philosophical argument about the impossibility of infinite finites.
Let's break that phrase down because infinite finites sounds like an oxymoron.
It is, and that is exactly their point. Think of it like a massive library. Imagine a library with an infinite number of books, but every individual book only has a limited, finite number of pages.
Okay.
The authors argue that while you can imagine this infinite library in your head, math and logic break down when you try to actually build it in physical reality. You cannot have an unlimited number of limited things. They argue that applying the concept of infinity to physical universes is a mathematical impossibility.
Their next critique is that the multiverse theory doesn't actually solve the problem of design, it just pushes it back a step.
Right.
Even if a multiverse generator exists, churning out infinite realities, the precise mechanisms required to generate universes like the extreme precision of the Big Bang itself would still require a finely tuned system. A machine that creates universes would still need a designer to build the machine.
But the critique they lean into most heavily involves what they see as a dangerous, moral, slippery slope.
Right. This is a heavy philosophical pivot in the text, but it's crucial to their argument. They use extreme historical examples to make their point.
They argue that if you embrace a theory where infinite universes exist and every possible event happens by chance somewhere, you destroy the concept of deliberate action. The text specifically points to the 9/11 attacks and the Holocaust. Geisler and Turek argue that under the strict logic of an infinite multiverse, someone could theoretically claim that we just happen to live in the specific universe where those massive horrors appear to be deliberate, coordinated acts of evil, but were actually just a statistical alignment of random atoms playing out by chance.
By taking the multiverse logic to its absolute, most extreme philosophical endpoint, the authors argue the theory multiplies absurdities, rather than answering the clear implications of a designed universe.
Which leads them to flip a very common cultural argument completely on its head. Usually in these debates, religion and theology are accused of relying on blind faith, while secular science relies on hard facts. But the authors conclude that, in this specific context, it is actually atheists who are relying on blind faith.
How so?
Well, their logic is that those who hold to the multiverse are putting their faith in unobservable, hypothetical theories that cannot be tested, whereas believers who look at the Anthropic Principle are relying on the actual observable mathematical improbabilities of the universe we can currently measure. The text frames the rejection of a designer not as a head problem, meaning a lack of intellectual evidence, but as a will problem, an emotional or philosophical refusal to accept where the data points.
This philosophical debate raises a really important question about how we actually perceive the world around us day to day. And this brings us to the final major theme of the text: scale, perspective, and the danger of the ordinary.
Yeah.
The text shifts our focus away from microscopic constants and mathematical formulas and looks at the sheer mind-boggling vastness of space. To do this, they reference the tragic loss of the space shuttle Columbia in 2003, quoting President George W. Bush's tribute to the crew, where he spoke about the profound darkness and danger beyond our world.
They use that imagery to try and help the reader grasp the absolute scale of the cosmos. They point out that in our Milky Way galaxy alone, there are roughly 100 billion stars, and the average distance between those stars is 30 trillion miles.
And crucially, the text notes that this 30 trillion mile distance is yet another anthropic constant. If stars were grouped significantly closer together, the gravitational pull between them would rip planets out of their stable orbits, creating chaos and making sustained life impossible.
To help us wrap our human minds around the distance of 30 trillion miles, the authors offer a brilliant, really humbling analogy.
Yeah, I love this part.
The space shuttle traveled at a speed of about 5 miles per second. If you had strapped into a space shuttle at the time of Christ, roughly 2,000 years ago, and started flying toward the nearest star at 5 miles per second, you would only be 1/100th of the way there today.
That's crazy.
It would take over 200,000 years of continuous travel to cross 30 trillion miles.
Furthermore, they note that the total number of stars in the observable universe is roughly equal to the number of grains of sand on all the beaches on Earth combined. Imagine spending 200,000 years traveling at 5 miles a second just to get from one single grain of sand to the very next grain of sand.
It is completely overwhelming to visualize, but the text argues that We rarely, if ever, think about this. They bring in a quote from C.S. Lewis's classic book, The Screwtape Letters.
Right.
If you aren't familiar, it is a fictional, satirical book written from the perspective of a senior demon named Screwtape, who is giving advice to his demon nephew on how to keep humans distracted from God. Screwtape advises the young demon to keep pressing home on him the ordinariness of things.
Ordinariness.
Yeah. The demon explicitly warns against letting humans look too closely at real science, because understanding the true mechanics of the universe will encourage them to think about profound realities they can't touch and see.
Zeisler and Turek used that C.S. Lewis concept to highlight a very real psychological tendency. We get so caught up in the fast-paced, mundane tasks of our lives, paying bills, sitting in traffic, that we look at this astronomically complex, mathematically impossible universe and we just consider it ordinary. Yeah. We take the sheer miracle of our continued existence totally for granted. But the book argues that those who are forced to get a different perspective, like astronauts, tend to see it very differently.
Yes, the text shares the famous anecdote of the Apollo 8 astronauts. When they became the first human beings in history to pass around the far side of the moon and see the Earth rise in the distance as tiny, fragile blue marble in a sea of blackness, they were so overwhelmed by the design and beauty of it that they took turns reverently reading from the book of Genesis on live television.
Wow.
The authors also quote astronaut John Glenn, who at 77 years old looked out the window of the Space Shuttle Discovery and simply said, "To look out at this kind of creation and not believe in God is to me impossible."
If we summarize the journey this text takes us on, it is a profound, meticulously detailed argument from design. The authors use the terrifying, deeply human narrative of the Apollo 13 crisis to illustrate just how delicate and interdependent the systems of our own planet truly are. They present the astronomical mathematical odds of the Anthropic Principle, arguing that 122 perfectly tuned constants point definitively to a cosmic designer. Furthermore, they assert that ignoring this observable evidence in favor of unprovable theories like the multiverse requires a leap of blind faith.
It's an argument that really demands you look up from your daily routine. It's so easy to fall into that trap C.S. Lewis described, just seeing the ordinariness of things. It is easy to completely ignore the sheer mathematical improbability that you are breathing the exact right percentage of oxygen, held to the ground by the exact right amount of gravity, protected by the exact right magnetic field, just to be able to listen to this right now.
Which leaves us with a fascinating final thought to ponder. We've talked a lot about the math and the physical laws today. But if the authors are right that our fast-paced lives make us blind to the incredibly fine-tuned miracle of the cosmos, how might deeply recognizing the precise, delicate balance of the universe change the way you interact with your own, seemingly ordinary, day-to-day environment right now?
That's a great question.
Thank you so much for joining us for this deep dive into the teleological argument. We hope this exploration of the science, the history, and the philosophy gave you some incredible new perspectives to consider. Keep asking the big questions.